All right, lesson 2. We're going to look at rates of change. Now, often in this class, you'll find out that we're not doing a lot of new types of math. So rate of change is not going to be a new thing and how to find it. It's just called something new. And what we used to call it is slope. So every time you see rate of change or find the rate of change, it's the same as finding slope. It's just a more real-life concept compared to just finding a slope of a line on a piece of paper. So rate of change could be used more with real life things. So we're kind of taking that new step towards using this stuff in more practical manners. Okay, so just think of that every time you see this, the rate of change. This looks very familiar right here. All right, that was the slope formula you knew probably since the 7th or 8th grade. Right now, it might look a little different. We'll call things a little different, but just keep in mind all you're doing is really finding slope. Right, so when we come down to our next problems, don't worry about the new notation and what things look like and how different it is. Just keep in mind it's something you are familiar with, and you're really just writing it down in a new way, kind of like translating it to a new language. All right, so let's find the first example here, which is just find the average rate of change. And how much is it changing, or what is the slope? And it gives you the two x values. So that's what these are right here. Right? Those are the two x values. And they don't give us what the y values are. Right? So we have to figure those out ourselves. But keep in mind, that's all we're doing. Right? So we're going to call this average rate of change instead of slope. And we just abbreviate AROC for average rate of change. Right? And we need to do over the interval, or the x values are going to be 1 and 3. And we usually do the second one minus the first one, right? So we're going to do 3 minus 1 for our x values, and we need the y value at 3, and that's the same thing as f of 3 minus f of 1. All right, so that's how you start the problem. It looks a little bit different. We don't actually use y1 and y2 so much. We use our new notation. Now, these mean the same thing. Y2 is the number at x equals 3, which is the same as f of 3. So off to the side, I just need to plug in 3 and find f of 3, right? Which is going to be 3 to the third power minus 4 times 3. So I'm just substituting in 3 for each of these x values, right here and here and here. So I have to simplify that, so I get 27 minus 12, which equals 15. So that's my first y value. That's like my y2 I just found. So I'm going to do this right here. I'm going to write, okay, 15, right, over 3 minus 1. And I don't know what my f of 1 is next yet. So I'm going to find what f of 1 is. Meaning, what's the y value when x equals 1? And you just do that by plugging in 1. So we got 1 cubed minus 4 times 1. So this is 1 minus 4. And we have negative 3. So I'm going to have 15 minus negative 3. And if you simplify that, that's going to be 18 on top, 2 on the bottom, which is 9. So my average rate of change from the interval 1 to 3, the x's from x equals 1 to x equals 3, is going to be 9. Right? Again, we didn't really do anything different, right? We could have erased this and said, find the slope, and that looks like a problem from the 8th grade. So just keep that in mind. The symbols are new, but what you're doing and the concept that you're doing is not new. All right, so now let's use it for a little bit more real-world concepts here, right? And it says find the rate of change for this particular problem from 1985 to 1990. Right? So it's giving you a lot of x values, and you just have to find the correct ones and use them. All right, so we're going to go right here. So from 1985 to 1990. Oopsie, let's use there we go. Let's use right here, 1985 to 1990. So these are the x values, and these are the y values. So we just had to use the chart to locate them. So of course, our x's are going to be right here. Get that turned off. These are x values, and these are our y values. All right, so we can do that. So the way we write this down is a little different, right? Find the average rate of change. So I'm going to say average rate of change equals, I'm going to use the second ones first. So I'm going to go 208.3 minus the first, 166.3, all divided by the 1990 minus 1985. And using a calculator, all right, we'll get our values and we punch it in here. And it looks like it comes about to about 8.4. Right? And we want to look at, well, 8.4 what? What are we talking about in this problem? This is what we're going to do that's a little bit different from before. We actually talk about what these answers mean. So 8.4 what? When we look at our units, right, and it's millions, right? So the top, this was 208.3 million minus 266.3 million. So the top units are millions. Million of what? All right, that's million tons. So I'm going to use the exact units that I see here. And what's on the bottom? What do these numbers represent? Right, well these are years, right? That's what all these are. It doesn't really list it here, but it says that's the year. So it's 8.4 million tons per year, or over years. All right, so this becomes more important when you get to pre-calculus of what these answers actually mean, and we got to have units on everything. All right, so that would be our final answer, the number with the units. All right, and it says, did the rate of trash ever decline in the 58 period? When? What was the average rate of change? When did this happen? All right, so we have the decline means to get smaller, right? So we're looking at these numbers and see, well, where did it get smaller? Where's it smaller here? So let's see here. This has gone up. No, like I'm just scanning each one of these and trying to find out, well, when did it get actually smaller? These got bigger, that got bigger, that's bigger. Keep looking, keep looking, keep looking. And then all of a sudden, right here, 253.7 million to 251. So it got smaller and then got bigger again. So we want to use these values over here, where it got smaller. So it's 2005 to 2010. All right, so I'm just going to do the same thing I did in part A and do it again in part B, just with the different numbers. All right, so we can go back and do that. So we have our average rate of change, once again, AROC equals, and the Y values first, second one first, 251.1 minus 253.7. All divided by, all over, the years, 2010, 2010, and 2005. There we go. Once again, you can use a calculator to figure out what this is. And the fact that we know that this is a decline, that tells us that we are expecting a negative answer here, right? It went down, so that means the rate that the rate of what trash we're making actually decreased. So this does come out to a negative number, and it's about 0.52. Yeah. And again, we've got to have the same units, right? Rate of change, and we got to write it out: million tons per year, over years. That's it. Okay, so we found the slope or rate of change, and we have the units on there also. Okay. So what does this actually mean? You know, what does it actually mean? That's, well, it went down by 500,000, right? This is 0.52. That's about half, right? 0.5 is half, so that means the rate of change, or the average trash went down about 500,000 from this time period, from this 5-year time period. Okay. All right, let's keep going. So after surgery, give them pain reliever like ibuprofen or something, and the medication decreases slowly over time. Let C of T represent medicine's concentration in your body. All right. Write an expression for the rate of change of the medicine's concentration over the period of T equals 15 to T equals 90 minutes. So if you took something to help the pain go down, like how much did it go down or change from after 15 minutes taking it to after an hour and a half, 90 minutes taking it, right? Well, how would you find that concentration? So you can see this would be important for like a doctor or a pharmacist, right, to know how long a medicine acts inside the body, especially if it's like an athlete, how long will it take them to recover, right? So again, we're getting more real world here. And it just asks us to come up with an expression. And the expression has a name, we call it C of T. Right? So we're trying to find the rate of change. So we're going to do this without actually having the values. So this is really asking us to write something like this, but without knowing numbers, we just put in some basic information like this. We'll have something like this instead, because we don't know what these values actually equal. Right, so here's what we're going to do. We're going to go say I know my average rate of change, right, equals, I know the time. I know it's from 90 minutes or 15 minutes to 90 minutes. So I know the bottom of this problem is going to be 90 minus 15. And then, of course, the y value, or the C of t value for 90. So C of 90, whatever that might be, doesn't give it to us, minus whatever the concentration was after 15 minutes. So we're taking the concentration after 90 minutes minus the concentration of this medicine after 15 minutes and dividing it by 90 minus 15. And that's all we could do here, just asking for this expression. And we would expect, since it's going down, the answer would be a negative. We don't know what it is, really, but since it's decreasing, we expect this average rate of change to be negative. All right, we could also talk about rate of change, of course, with traveling in a vehicle, right? How fast you're going. So you can see we have a chart here about how far someone's driven and how long it took them to drive there. Of course, this is in distance is in miles, and this one's in minutes, right? Not quite the units we're used to. Of course, when we're driving, usually it's miles per hour, not miles per minute. All right, but that's okay. So it says, let's explore over this 2-year period, what's the average rate of change that the car travels? All right, so well, from where to where? So if it just says, in general, what's the average rate that the car traveled, that's from beginning to end. So you have to infer, you have to be pretty good at our language skills here, so beginning to end. So what are those values? Well, that'd be at the beginning right here, right, and at the end, which is 120, right, way up here. So my x values are 0 and 120. So average rate of change, all right, from 120 minus 0. And the distances traveled. Well, now at 120, it looks like we traveled 100 miles. And of course, after 0 minutes, we haven't traveled anywhere, right? 0, 0. So if we simplify this, it becomes 5 over 6. Now, this is in minutes per mile, right? Which is not really a good unit, so we like to have a useful unit. Let's make this in miles per hour. So if we go 5, 6, right, which is a little less than 1 minute per mile, 1 mile per minute. How fast is that going? So let's multiply this by 60, right, and that'll give us miles per hour. Right, now let's look at this as units. So remember, the top is minutes, and the top is miles. Yeah, miles. Try that again. Miles. And the bottom is minutes. Right? So this is saying every 5 miles, you go 5 miles every 6 minutes. It's not really a good indicator of how fast you're going. So that's why I want to convert this to multiply this by 60 minutes in 1 hour. So I'm just converting the minutes into hours. So when I cancel this, I'll get, minutes cancel out. And 6 goes into 60 10 times. So I have 5 times 10. 5 times 10. And that's miles now per hour. So I converted it to something that's a little more realistic. All right, miles per hour, or mph. All right, so let's continue doing this. And we'll continue converting it to miles per hour just to make it more realistic. Everybody likes, well, when are we going to use this in the real world? Well, in the real world, we have to put things in different units. Because you're like, well, why do we have to change this? because no one talks about how many miles they go in a minute, right? So we have to make sure it makes sense. All right, so let's just look at, let's see here, from after 30 minutes to after 60 minutes, after an hour, right? So now we're going to do the same thing, 30 minutes and 60 minutes. So I'm just finding the slope, really, of a line that connects these two, if you want to think about it this way. Oopsie. What I'm really doing is when I find the rate of change, I did it again. Imagine just drawing another line that connects these two dots and finding the rate of change, finding the slope of it. Okay. So we want to calculate it. You could also do rise over run. You could say we're going up 20 over 30. Right? That would work. Because we're going up 10, 20 over 10, 20, 30. So 20 over 30. Right? But we want to calculate it as well. So we want to show that in calculation form. So we're going to do, looks like 40, right, minus 20, that's the distance in miles, over 60 minus 30 minutes. And sure enough, we get 20 over 30, just like as if we did the rise over run, up 20 over 30. All right, and this will reduce, of course. We're going to reduce that. That's 2 over 3. But we want to also convert that like we did before. Just multiply it by 60. I multiply that by 60. That's going to give us, let's see here. Let's see, 30 goes into 60 2 times. So 2 and 20, multiply those, you get 40. Remember, that's miles per hour. So during that time, I was driving an average of 40 miles per hour. Okay, so for a whole half hour. Now think about the real context. Like what kind of drive do you think this is? All right, you're driving an average of 40 miles per hour for a whole 30 minutes. That's not a very fast pace, but if you ever driven, like, let's say in the mountains or in rain or in snow, yeah, you could see yourself driving 40 miles per hour for a whole half hour because you have to drive a little slower for all the winding turns in the mountains, or driving slower if it's really snowing or raining. So think about the real life context here. All right, next it says, when is it traveling the fastest? How fast was it traveling? So fastest, right, fastest. What does that actually mean mathematically? Highest rate of change, aka, highest slope. So we're looking at the graph, where is the slope the highest rate of change? All right, so we probably use between right here and right here, right? That's the steepest part of this entire graph, from 70 minutes to 90 minutes. For those 20 minutes, that's when we're going the fastest. How fast were we going that time? All right, so what was the average rate of change during that time? All right, from 90 minutes and 70 minutes, 70 to 90 minutes over that 20-minute period. And we were going, let's see here, 80, looks like 80, and right here we have, let's say that's 50. Okay, and simplify once again. We have 30 over 20, and let's convert that to, convert that to miles per hour. So we have 20 going into 60 3 times, and 30 times 3 is 90 miles per hour. That's really fast. Hour. Okay. Keep on going, and it says, what's the slope of the graph represented from 90 to 120? What does the slope mean in the context of the problem? All right, so we're just keep on doing more practice, looks like here. So 90 to 120. Okay, so that's right here. All right, for this one, how about we just do it off the graph? How about that? So this time, I'm just going to do, it goes up from 80 to 100, right? That's 20. And it's the same thing as doing 100 minus 80. That's the top of the problem, right? That's the numerator. So I can either count 20 by going up 10 again, or if I subtract 100 minus 80, that's also 20. So here I could say average rate of change. It's going to be 20. And how many minutes was that over? From 90 to 120. 90 to 120. How many minutes is that? That is 30 minutes. So we got 30 minutes. So this looks familiar. Okay, so multiply that by 60 once again, and we have, looks like 40 again. Miles per hour. There we go. What does it mean? Okay, so it means from at an hour and a half to 2 hours, right? Because 90 minutes is an hour and a half, and then 120, that's 2 hours exactly. So from an hour and a half to 2 hours of the trip, we're going about 40 miles an hour again, on average. All right, and it says, lastly, what's the speed of the car at 45? All right, so at 45, that's somewhere right in between here. So how can we find that? So we're just going to use, let me get this stuff off here. We want to do 45, that's right here. So all we can do is really find, well, right here, and use those, and since these are on a straight line, right, it'll give me what's happening at 45. That's the average for everything from 40 to 60, including 45, 50, 55. Since they're all on a straight line, it's going to be the same average rate of change. All right, so I really just have to find the average rate of change from 40 to 60. And I want to use those because I actually have perfect numbers here. Like this is going to be 30, right? And I'm not dealing with any fractions, and it's going to be 40. So we got up 10 over 20, up 10 over 20. Okay, and multiply that by 60 again. That goes 3, so we have 30 miles per hour. And sometimes you'll see it written as mph, so these are the same thing, miles per hour, miles per hour. All right, same meaning. All right, so as you can see, we're just doing the same thing we've done before with slope, but we have to understand things such as, well, can I find 45? Well, it's on the same straight line. So it's not really like new math, but it is a new understanding on how things work with charts and graphs. Okay? But just keep doing the same type of rise over run, or using that slope formula. Just remember, we're now calling average rate of change from now on, because it's how fast something is increasing or decreasing. Okay, that's it for now.